Have you ever wondered what makes up most of our universe, and why we can't see it? Imagine a cosmos where the vast majority of matter and energy is invisible, yet shapes everything we know. Galaxies swirl, stars shine, and space expands, all under the influence of forces we can't touch or see. Today, we're diving into 100 fascinating facts about dark matter and dark energy, the mysterious ingredients that dominate our universe and challenge everything we thought we knew. Fact 1. The universe is mostly invisible. Did you ever look up at the night sky and think, wow, the universe feels huge? Stars everywhere. Galaxies so far away they look like tiny sparkles frozen in black space. But here's the twist. You're only seeing a tiny slice of reality. Like, not even the juicy part of the cosmic cake, more like the crumbs on the plate. We humans trust our eyes so much. If we can see it, it's real. If we can't, well, maybe it's not there. But space doesn't care about our feelings. Most of the universe, almost 95%, doesn't shine, doesn't glow, doesn't reflect light, and doesn't behave the way familiar matter behaves. And that means our telescopes, our cameras, even our eyes, they miss nearly everything. It feels almost unfair, right? You stare at this beautiful sky, and it's lying to you. All those stars and planets, they're just ordinary matter, a tiny fraction of existence. The rest? A silent kingdom hiding in plain sight. Dark matter and dark energy. Stuff we know is out there, not because we see it, but because everything else acts weird without it. Imagine going into a room, the furniture is moving by itself, and gravity feels wrong, but the room looks empty. That's the universe for astronomers. They see galaxies swirling too fast, light bending strangely, space itself stretching, and they know something invisible is pulling strings. And here's the funny part. The ordinary stuff we're so familiar with, atoms, stars, planets, us, we're cosmic minorities. We're like a tiny guest in someone else's massive house. A guest who turned on the lights and said, "Oh nice, I see everything," while really seeing almost nothing. It's humbling, it's thrilling, and honestly, it's kind of creepy too, because it means reality is deeper, stranger, and far more mysterious than anyone imagined. The universe keeps secrets, not because it wants to hide, but because we just started learning how to look, and this is only the beginning. The moment you realize most of reality is invisible, every star feels like a clue, every galaxy a puzzle. We don't just live in space, we live in a mystery story. Fact 2. Dark matter versus dark energy. The core difference. Okay, so picture this. The universe is like a giant cosmic tug-of-war. On one side, you have gravity pulling things together. On the other side, something else is pushing everything apart, and both forces are invisible. Sounds dramatic, right? Welcome to dark matter and dark energy. Cousins, but not friends. Let's keep it simple. Dark matter pulls, dark energy pushes. Dark matter is like a hidden glue. It doesn't shine or glow, but it keeps galaxies together. Without it, stars would fling into space like kids jumping off a merry-go-round gone wild. We discovered dark matter because the universe behaved like someone added secret weight everywhere. Invisible weight. Heavy and quiet. Dark energy, on the other hand? It's like the universe hit the gas pedal and forgot to let go. It stretches space itself, making galaxies drift apart faster and faster. The weird part, nobody expected that. Scientists thought gravity would slow the universe down. Instead, something unseen is speeding it up, like an engine we can't locate. So yeah, they sound similar, both dark, both mysterious. But they do opposite things. Dark matter builds the cosmic web, holding galaxies in place. Dark energy tears space wider, pushing galaxies apart like they're politely trying to avoid each other forever. Think of dark matter as the universe's quiet architect, and dark energy as the unstoppable expansion force painting space bigger by the second. Two invisible powers shaping everything, and we're just learning their names. Fact 3. What we can see versus what we cannot. Let's do a little imagination exercise. You walk into a bakery, you see the donuts, the pastries, the cake slices. Everything looks delicious, but the smell, that warm sweet smell, that's invisible. And behind the wall, ovens, dough, ingredients, flour flying everywhere. The real work happens where you can't see it. The universe works the same way. We see stars, planets, gas clouds, galaxies. Pretty stuff, glowing stuff, but most of the universe doesn't shine. Dark matter doesn't glow. Dark energy doesn't shimmer. Yet they run everything. The way galaxies spin, how space stretches, even how time unfolds. Think about light for a second. Our eyes evolved to see this tiny slice of electromagnetic waves. Just a sliver. We can't see radio waves, X-rays, gamma rays, but they exist. So why assume space only contains things we see? Most of existence hides behind the curtain, and honestly, it makes everything more magical. There's comfort in mystery, in knowing the universe is bigger than our senses. One day, maybe we'll see the unseen, or maybe reality always stays one step ahead, reminding us to stay curious. Either way, we're living inside a world of shadows and secrets, and every telescope is a flashlight into the unknown. Fact 4. The first hints of the unseen universe. Imagine being an astronomer in the early 1900s. You're staring at swirling galaxies, charting star speeds, thinking physics has things mostly figured out. And suddenly, the stars don't behave. Galaxies spin too fast. Mass calculations don't add up. Something invisible is messing with gravity. That's how the mystery began. Not with science fiction, but with confusion. Astronomer Fritz Zwicky first noticed it. He saw galaxy clusters moving like someone added secret mass. He called it Dunkelmaterie, dark matter. People shrugged. Science wasn't ready to accept the invisible yet. Then in the 1970s, Vera Rubin looked again. She saw stars orbiting galaxies at speeds that made no sense. They should have flown off into space, but didn't. The universe was cheating physics, or hiding something. Rubin didn't whisper her discovery. She pushed it into the spotlight. This wasn't mystical or magical. It was math screaming for answers. Light bending strangely. Galaxy speeds misbehaving. The universe leaving breadcrumbs. And later, that wild discovery that the universe is expanding faster. Dark energy walked into the story like a plot twist nobody wrote. Science didn't find the unseen universe in one moment. It slowly stumbled into it, one strange observation at a time. The cosmos doesn't reveal secrets loudly. It leaves clues, and we follow. Fact 5. Why we call it dark. Now don't picture dark like spooky or evil. Space isn't haunted. Well, probably. The word dark here simply means we can't see it. No light, no glow, no reflection, just invisible influence. It's like calling someone quiet, not because they're secretly plotting something dramatic, but because they just don't speak out loud. Dark matter doesn't talk in light. Dark energy doesn't dance in photons. The truth. Scientists didn't name it to sound dramatic, though it does sound cool, right? Dark matter feels like something from a fantasy movie. But the name is humble. It just means unknown, hidden, waiting. We don't know what dark matter is made of. We don't know what dark energy really is. We don't even fully know why they exist. And until we understand them, dark is the most honest label we have. One day, we might rename them when the mystery fades. But for now, darkness isn't fear. It's curiosity. It's a reminder that even with telescopes reaching billions of light years away, the universe still whispers instead of shouts. And honestly, that makes exploring it so much more fun. ChatGPT said, Fact 6. Dark matter makes gravity stronger. Dark energy pushes things apart. Imagine the universe as a giant playground. On one side, you have the force that loves pulling everything together. That's gravity, and dark matter boosts it. On the other side, you have something like a never-ending push that keeps stretching everything apart. That's dark energy. Dark matter behaves like a quiet helper of gravity. It gathers around galaxies, wraps them in invisible halos, and says, "Hey, stick together, don't go flying off." If dark matter didn't exist, stars would spin right out of their galaxies like marbles flinging off a spinning plate. Gravity needs backup, and dark matter provides it. Silently, without any sparkle or light. Dark energy is the total opposite. If dark matter is the universe's glue, dark energy is the universe's expansion button, stuck on maximum. It doesn't just push objects away, it pushes space itself to grow bigger. Which is wild when you think about it. It's like stretching a sheet of dough, except the dough keeps stretching faster the more you pull it. And here's the strange part. They're both invisible. They don't act like anything we're familiar with. They don't shine, they don't absorb light, and they don't interact with normal matter the way we expect, but they shape everything. One builds cosmic structures, the other pulls them apart. It's like the universe is in a constant dance between holding on and letting go. We live in the middle of that tug of war, and every galaxy, every star, every particle exists because these two unseen forces balance just enough to allow space and life to unfold. Fact 7. Most galaxies wouldn't exist without dark matter. Let's imagine building a sandcastle by the beach. You pile wet sand, shape the towers, carve the walls. But what if every grain of sand wanted to roll away? What if the castle wouldn't hold? That's galaxies without dark matter. Galaxies spin fast, like seriously fast. Stars orbit the centre at such speeds that gravity alone shouldn't hold them in place. They should scatter, drift, fly off into space, leaving empty darkness behind. But that doesn't happen. Instead, galaxies stay beautifully held together. Why? Because dark matter is there, adding invisible mass and strength to gravity, keeping everything tight. Think of dark matter as a giant invisible scaffold around each galaxy. We can't see it, but stars feel it. They move like they're swimming through a thick, unseen ocean that hugs them together. Without it, there would be no spiral galaxies like the Milky Way, no cosmic cities of stars, no clusters stretching across the universe like glitter frozen in motion. It's strange knowing we owe our galaxy's existence, and our own, to something we can't detect directly. It humbles you, makes you wonder how much of reality hides behind a curtain we don't yet know how to lift. One day we may finally understand what dark matter really is, but for now we just know this. It's the quiet builder of the universe, and without it, the sky would be empty. Fact 8. The universe is 95% unknown. Take a moment and glance around your room. Everything you see, your phone, your hand, the light, is made from ordinary matter, atoms, particles, visible reality. Now, imagine finding out that all of that only makes up about 5% of the universe. 5%. The rest? A giant cosmic mystery. Dark matter and dark energy own almost everything. It's like living in a mansion and only understanding one tiny corner of one room. Every star we've ever admired, every galaxy ever photographed, every nebula glowing in telescope images. They're the minority. The universe is mostly made of things we can't see, can't touch, and barely understand. It's unsettling at first, but also thrilling. We aren't at the end of science. We're still at the beginning. The unknown isn't a wall, it's an open door. Behind it, discoveries wait that could change everything. Physics, space, maybe even how we understand existence. We humans love to feel like we have all the answers. But the universe smiles back and says, "You've only seen the introduction. Keep reading." Fact 9. Ordinary matter is the exception, not the rule. We tend to assume what we see is normal. Planets, stars, atoms. That must be what most of the universe is, right? Turns out reality has a sense of humour. Ordinary matter, the stuff that builds everything familiar, is rare. Most of existence doesn't glow. It doesn't form atoms. It doesn't follow the rules we learned in school. It exists in the shadows, shaping the cosmos without ever showing its face. We're made of cosmic minority material. That makes life feel special, doesn't it? Like we're rare gems in a universe full of invisible oceans. But it also reminds us that our perspective is tiny. We evolved to navigate Earth, not the vast cosmic unknown. So our senses see a sliver of truth, enough to survive, not enough to understand everything. Every time we look at the sky and think, that's the universe, we're really looking at a tiny island in a massive hidden ocean. And that makes our curiosity more important than ever. We aren't just trying to learn about space, we're trying to discover what reality really is. Fact 10. The cosmic mystery. Scientists still struggle to solve science usually works like this. Observe, test, explain, repeat. But dark matter and dark energy broke that formula. We observed effects, tested theories, and nothing fits perfectly. We're staring at a universe that behaves like it has secrets written in invisible ink. Every time scientists think they're close to understanding, a new piece doesn't match. The equations resist. Experiments whisper, instead of shout. The more we learn, the deeper the puzzle grows, and that's not a failure, that's the thrill of discovery. Think about humanity's big leaps: electricity, DNA, atoms. Each one felt impossible before we figured it out. Now we're facing the biggest mystery yet. What is most of the universe made of? What force drives expansion? Are we missing whole new laws of physics? Some nights, astronomers must feel like detectives with half-burned clue cards in a case that refuses to close. But they keep looking, keep measuring, keep wondering. Because the moment we solve this, everything we know about reality could shift. The universe is whispering, and we're learning how to listen, slowly, patiently, bravely. Fact 11. Not made of atoms. Let's start with something familiar. Atoms. They're our building blocks. Tiny particles making up everything you can touch, hold, or bump your knee on. Your body? Atoms. Your phone? Atoms. The sun? Yep. Atoms again. We got comfortable thinking atoms were the foundation of reality. Then dark matter shows up like an unexpected guest at a family reunion and says, "Oh, atoms? Cute, but I don't do that." Dark matter isn't made of atoms at all. No protons, no neutrons, no electrons floating around like little planets. It doesn't form elements, molecules, or anything we recognize as solid or liquid or gas. It's like a whole other category of stuff the universe decided to throw in just to keep us humble. So, if it's not atoms, what is it? That's the mystery. We have theories, exotic particles, invisible fields, but nothing we've confirmed. Dark matter lives in a world beyond chemistry and biology. It doesn't care about bonding or reacting or glowing. It just exists, quietly shaping the universe while atoms do their dramatic visible dance. It's a wild thought. Most of the universe doesn't follow the same rules as the matter we're made of. We may be the odd ones, living in a tiny bubble of atomic reality inside a much stranger universe. Fact 12. Not stars, planets, or black holes. There was a time when scientists thought, maybe dark matter is just stuff we can't see, like faint stars or dead planets or hidden black holes. Seems logical, right? Invisible things could just be regular things we haven't detected. But no, we checked, we scanned the sky, we counted stars, we searched for faint objects, compact dead stars, rogue planets, hidden black holes. Those things exist, but not nearly enough to explain the cosmic math problem we're facing. Dark matter isn't made of the same celestial objects we know. It's not just hiding in shadows, it's fundamentally different. We're talking about something everywhere, woven into galaxy halos, shaping cosmic structure, yet totally unlike the familiar universe. It's as if someone designed a separate collection of matter, invisible and untouchable, running on different physics. Not stars, not planets, not black holes. Something else entirely. Something new. When science eliminates the ordinary, all that remains is extraordinary, even if we don't understand it yet. Fact 13, invisible, does not emit light. When we think of seeing, we think of light. Vision is basically light bouncing off things into our eyes. Telescopes? Same story. They hunt for light. But dark matter refuses to play along. It doesn't shine. It doesn't glow. It doesn't reflect. It doesn't absorb. It's not hiding light. It simply has none. That means if dark matter passed right in front of you, you'd see nothing. No shimmer, no shadow, no hint. It would be like looking at empty space even though something massive was right there. It makes you wonder, how much of life depends on what we can't see? We trust sight so much, but the universe reminds us, vision is limited. Reality doesn't care if it's visible to human eyes. The world is bigger than our senses, and dark matter is proof. Sometimes the most powerful forces are the quietest ones. Just because something doesn't shine doesn't mean it isn't shaping everything. Fact 14. Detected only through gravity. If we can't see dark matter, how do we know it exists? Gravity. The universe's truth serum. Stars move in ways that make no sense unless something heavy, invisible, is nearby. Galaxies bend light around them more than they should. Galaxy clusters behave like they're carrying secret weight. That weight? Dark matter. Gravity betrays it. It's like watching leaves swirl on a windy day. You don't see the wind, but you know it's there from the way things move. Dark matter pulls on stars, bends space, and influences motion. We don't see the thing. We see its effect. In a way, dark matter is like a quiet, forceful presence in a room. It never speaks, never shows itself, but every object moves differently because it's there. We understand enough to know it exists, but not enough to say what it is. Yet. Fact 15. Makes up 27% of the universe. Imagine slicing the universe like a cosmic pie. One slice, about 5%, is everything we know: stars, planets, galaxies, us. Another slice, and nearly 27%, is dark matter, and the biggest slice, dark energy, taking the rest. The dark matter isn't rare. It's everywhere, surrounding galaxies, filling space, shaping cosmic history. If we could see it, the universe wouldn't look like a sprinkle of stars on black velvet. It would look like a massive glowing web, strands connecting galaxies like beads on invisible strings. 27%. It's funny. We spend all our time studying ordinary matter, when it's not even close to the main character. We're studying the supporting actor while the lead is backstage, silent and mysterious. One day, when we understand dark matter, science might look back and say, that was the turning point. The moment humanity realized it was studying only the edges of reality, and we're living in that moment right now. Fact 16. Halos of dark matter surround galaxies. Picture a galaxy. You probably imagine a flat spinning spiral, stars glowing, dust swirling, like a cosmic whirlpool frozen in space. But that's only the part our eyes can see. Around every galaxy, including ours, there's something bigger, rounder, and completely invisible. A dark matter halo. A halo isn't like a ring or a donut shape. It's more like a giant sphere of unseen mass that wraps the whole galaxy like a protective bubble. If you could see dark matter, a galaxy would look less like a thin disk and more like a glowing egg inside a huge ghostly sphere. Why do these halos matter? Because they keep galaxies alive and stable. Without dark matter halos, galaxies wouldn't form the way they do. They wouldn't stay together. Stars would scatter. Gravity wouldn't be strong enough. And the universe would look like a lonely soup of stray stars instead of the beautiful cosmic cities we see in telescope images. Dark matter halos are like the scaffolding of the universe, the invisible framework holding everything in place. It's fascinating and a little eerie. Most of what shapes galaxies can't be seen, touched, or detected with light, yet it's there, silently cradling billions of stars. Sometimes the most powerful structures aren't the ones that shine, they're the ones that hold the shining things together. Fact 17. The Milky Way moves inside a dark matter bubble. We like to think of the Milky Way as a grand spiral floating all alone in space, but it isn't drifting naked and free. It's actually inside a giant bubble of dark matter, like a fish swimming inside an invisible aquarium. This bubble stretches way beyond the stars we can see. If the Milky Way were the size of a dinner plate, the dark matter bubble around it would be the size of a house. It's that huge. And here's the wild part. We're not just sitting inside this bubble, we're moving through it, orbiting, travelling, floating in a sea of unseen gravity. Every star, every planet, every spaceship, every atom in your body is riding through this silent ocean of mystery material. You, right now, are inside a cloud of something unknown. It's not spooky, it's spectacular. It means the universe is layered, like reality has hidden rooms we haven't explored yet, and the Milky Way is just one ship on this invisible tide. Being wrapped in something we can't see makes space feel bigger and stranger. It reminds us that we don't just live in the universe, we're surrounded by things we don't yet understand. Fact 18. Slower star rotation. Mystery solved by dark matter. There was once a cosmic head-scratcher that bothered astronomers for decades. When they measured how fast stars move around galaxies, they found something weird. Stars far from the centre were moving way too fast, like cars speeding on ice but somehow never sliding off the road. In normal physics, the farther a star is from the galaxy's centre, the slower it should orbit, just like planets in our solar system. But galaxies didn't follow the rules. Outer stars moved as fast as inner ones, and nothing made sense. Until dark matter came in like, "Hi, Yes, I explain this. Those outer stars weren't defying gravity. They had extra gravity helping them, coming from the invisible dark matter surrounding the galaxy. It was the missing mass in the equation, the hidden anchor, the unseen force saying, "No star flies away on my watch." Dark matter didn't just fix a mystery, it exposed an entire universe we had overlooked. One strange observation opened the door to discovering something bigger than our imagination. Sometimes, confusion is just the beginning of understanding. Fact 19. Dark matter keeps galaxies from flying apart. If dark matter disappeared right now, the universe would tear itself apart. Galaxies like the Milky Way would unravel like thread pulled from a sweater. Stars would drift off into the darkness, never forming patterns again. Solar systems wouldn't stay together. Planets might never form. Life probably never appears. Dark matter isn't just extra weight, it's the glue of the cosmos. We often think light is what makes the universe beautiful, but structure, shape, stability, that's dark matter's job. If galaxies are cosmic cities, dark matter is the gravity architecture holding them up. It's poetic in a way. The strongest cosmic force we depend on is the one we can't see. The universe doesn't stay together because it shines. It stays together because of a silent force in the dark. Isn't that strangely beautiful? What holds the universe together isn't the light we admire, but the invisible foundation beneath it. Fact 20. Galaxy clusters. Reveal its presence. One galaxy is already mysterious. But when you look at clusters of galaxies, giant gatherings of hundreds or even thousands of galaxies, the dark matter story becomes undeniable. Galaxies and clusters move so quickly that without something extra holding them together, they would fly away from each other like marbles exploding off a spinning plate. But they don't. They stay grouped, tightly, powerfully. Astronomers measured the mass of these clusters using different tools: star motion, gas temperature, gravitational lensing, and every method pointed to the same answer. There is way more mass than what we can see. Something huge, silent, and invisible is binding entire galaxies into families. Clusters are where dark matter leaves its fingerprints. You don't need to see it. You see the universe bending around it. Light curves, gravity deepens, motion obeys unseen weight. It's like watching ships move on an ocean and realizing the ocean exists not by seeing the water, but by seeing the waves. Dark matter doesn't ask to be seen, it just shapes everything anyway. Fact 21. WIMP's theory. Weakly interacting particles. Picture this. The universe is full of invisible particles, quietly drifting, barely touching anything, yet holding galaxies together. Sounds like something from a sci-fi movie, right? But for years, this was one of the most believed ideas in physics, the WIMP's theory. WIMP stands for weakly interacting massive particles. Catchy? Maybe not. Mysterious? Absolutely. Scientists thought WIMPs might be like shy giants, heavy, powerful, but barely interacting with ordinary matter. They could slip right through you, through planets, even through stars without leaving a trace. But their gravity, that would still count. That gravity could explain why galaxies don't spin apart and why space behaves like it's filled with extra invisible mass. For decades, physicists built detectors deep underground, inside mountains, in old mines, places protected from cosmic noise. They waited for WIMPs to bump into an atom just once. Imagine waiting years for a single tap. That's how big this hunt is. But here's the twist. So far, silence. No clear sign. It doesn't mean WIMPs don't exist, but it means if they do, they're even sneakier than imagined. Some scientists still believe in them. Others say it's time to move on. But the idea shaped the entire dark matter field. It told us one thing clearly. If dark matter exists, it's nothing like what we know. And honestly, that mystery is half the thrill. Fact 22. Axions, super tiny theoretical particles. If WIMPs are the big, strong, silent type, axions are the complete opposite. Tiny, delicate, almost ghost-like particles. Axions were first invented to solve a totally different physics problem, not dark matter. But funny enough, they turned out to be perfect candidates for the invisible stuff filling the universe. Imagine a particle so light that trillions could pass through you and you'd never know. They might not be rare, They might be everywhere, flooding the universe like a quiet ocean of energy. Some scientists think axions could form waves, moving through space smoothly like ripples in water. How do you catch something so small and soft? With extreme tricks, powerful magnetic fields, ultra-sensitive detectors, and patience. Lots of patience. It's like trying to hear a whisper in the middle of a hurricane. Axions are still hypothetical, but they keep getting more attention. Some experiments claim tiny hints. Nothing confirmed, but enough to keep the chase alive. If axions are real, the universe is whispering to us, we just need the right ears to listen. Fact 23. Sterile neutrinos. Neutrinos already exist. We've detected them. They're tiny, ghost-like, and pass through your body by the billions every second. But sterile neutrinos? They're like the secret shadow cousins of normal neutrinos. They wouldn't react to anything except gravity, and maybe not even that much. Imagine particles so disconnected from reality that they barely belong to it. Strange idea, definitely. But sterile neutrinos could explain dark matter without inventing brand new physics, just adding a mysterious twist to something we already know. There have been weird hints in neutrino experiments, tiny deviations that don't fit normal physics. Some scientists whisper, maybe that's them. Others say it's just noise, the truth, unknown. But if sterile neutrinos are real, they would rewrite physics textbooks overnight. It's not often one invisible particle reveals another even more invisible one. But hey, the universe loves secrets. Fact 24. Machos. Early rejected candidate. Before dark matter became exotic, scientists started simple. They asked, maybe it's just normal stuff we can't see, like faint stars, rogue planets, or black holes. These were called machos, massive astrophysical compact halo objects. Basically, the universe's junk drawer, lost stars, wandering planets, leftover cosmic debris. It made sense at first. Why invent new particles when old, boring objects might do the job? But as studies improved, the math didn't add up. There simply weren't enough hidden objects to explain all the extra gravity we saw. Machos helped explain some effects, but nowhere near enough. In a way, machos were the safe and simple guess. But the universe isn't simple, so scientists moved on to stranger possibilities. And that's how we ended up talking about axions, WIMPs, and ghost neutrinos instead of lost planets. Sometimes science progresses by ruling out what isn't there. Fact 25. Primordial black holes idea. Now this idea is wild. What if dark matter is actually made of black holes? Not the big ones at galaxy centers, but tiny ones created right after the Big Bang. We call them primordial black holes. Imagine baby black holes popping into existence before stars, before galaxies, before everything. Tiny, ancient, impossible to see, but powerful enough to tug on space. It sounds crazy. Yet it's one of the few dark matter ideas that doesn't require inventing new particles. The universe already knows how to make black holes. There's a catch, though. If too many existed, we'd notice them warping light, colliding, or making weird gravitational signals. But what if just the right amount exists, hiding perfectly in the background? Some recent research hints at possibilities, not proof but curiosity fuel. If primordial black holes are real, they aren't just dark matter, they're the universe's oldest survivors. Tiny scars left from the birth of time itself, and honestly, that might be the most poetic answer of all. Fact 26. Supersymmetric particle candidates. Have you ever heard the idea that every particle in the universe might have a secret twin? Sounds like something from a Marvel movie, but for years physicists truly believed it. This idea is called supersymmetry, or SUSY for short, and it changed the way scientists thought about dark matter. In supersymmetry, every known particle has a partner. Electrons, they get selectrons. Quarks, they get squawks. Yes, the names get funny, but the idea was serious. These partner particles could be heavy, stable, and nearly invisible. The perfect dark matter ingredients. The most famous candidate was the neutralino, a particle that could fill the universe, push galaxies into shape, and still slip right through your hand without a sound. For a long time, SUSY was the leading theory. People expected to find these particles at the Large Hadron Collider, the giant underground machine in Europe that smashes particles like cosmic bowling balls. Scientists waited. They listened. They ran experiment after experiment, and then nothing. No supersymmetric particles showed up, not a single one. But here's the thing, science doesn't give up that easily. Some say Susie still exists, just in a more hidden form. Others think we were looking in the wrong way. Or maybe the universe is stranger than Susie ever dreamed. That's the fun part. Every failure narrows the path, pointing us toward deeper truth. So supersymmetry remains suspended in this strange space between hope and doubt. It hasn't disappeared, it just sits quietly, a theory waiting for its moment, or its replacement. Sometimes in science, the silence is louder than the discovery. Fact 27. Unknown exotic particle possibilities. Okay, pause for a second and imagine this. What if dark matter isn't something elegant like Susie expected, but something totally bizarre? A particle we haven't even imagined yet. It's kind of humbling, right? We name our theories like we understand everything, but the universe doesn't owe us familiarity. Dark matter might be something exotic, something that doesn't follow our rules at all. Maybe it's not one particle, maybe it's many, maybe it's unstable, flickering in and out of reality like quantum ghosts. Maybe it interacts only through forces we don't know exist yet, or maybe it doesn't interact at all. Maybe it just bends space by existing. Scientists sometimes joke, dark matter could be anything as long as it's dark and it matters. It sounds funny, but it's also terrifying. When you don't know what you're looking for, every direction feels like both a clue and a dead end. But that uncertainty, it's also thrilling. Imagine being among the first humans trying to identify an entirely new kind of matter, a new chapter of physics, a brand new layer of reality. Sometimes progress doesn't come from knowing, but from admitting how much we don't know. Fact 28. Dark photons theory. You know regular photons, the particles of light that help you see everything around you? Now imagine their secret twin, a dark photon, moving through a hidden universe we can't touch. If ordinary light shapes the visible world, dark photons could shape the invisible one. It's a bold idea. What if dark matter has its own force, like our electromagnetic force, but hidden from us? Dark photons would be the messengers of that dark force, whispering across a world we cannot see. This theory tries to solve a puzzle physicists keep running into. Dark matter behaves too neatly. It clumps. It forms structures. It acts like it has rules. That hints at communication, at forces we don't feel. Dark photons could be the key. Detecting them, though, that's like trying to catch a shadow of a whisper. Researchers build delicate detectors, run laser experiments, study cosmic rays, and sift through data for tiny glitches that say, hey, something invisible just nudged reality. So far, just hints, tiny wiggles in the numbers, nothing solid yet. But the search continues. If dark photons are real, they don't just explain dark matter. They suggest an entire hidden world operating right beside ours, quiet, powerful, and unseen. Fact 29. Hidden mirror universe concept. This idea is probably the closest science ever gets to sounding like pure science fiction. What if there is a mirror universe overlapping ours? Not a parallel universe like in movies where you have an evil twin. No, a universe where matter exists but it doesn't talk to us. A shadow world, a ghost universe. In this mirror universe, particles could look like ours, behave like ours, maybe even form stars and galaxies, but their light wouldn't reach us. Their energy wouldn't warm us. Their atoms wouldn't collide with ours. We'd share the same cosmic space, but never touch. Some scientists think dark matter could simply be matter, just mirror matter. Everything we feel gravitationally, but nothing we see. It sounds unbelievable, and yet the math works more neatly than you'd think. Nature loves symmetry. Why not symmetry on the scale of reality itself? If true, then our universe isn't alone. It's half of a bigger cosmic system, like two languages written on the same page, but only one we can read. And one day, someone might find a way to whisper across the boundary. Fact 30. Could dark matter be a field instead of particles? We've spent decades chasing particles, WIMPs, axions, neutrinos, and sometimes the universe feels like it's quietly laughing at us. Because what if we're looking in the wrong direction entirely? What if dark matter isn't made of particles at all, or it is a field? something everywhere, stretching through space like a silent ocean. Not little dots, but a continuous presence like gravity or magnetism, a cosmic texture shaping reality from beneath. Fields don't collide, they don't leave tracks, they don't hit detectors, they just are. That would explain why dark matter is so hard to find. It would also mean the universe has a background layer we never noticed, like discovering the air after believing we lived in a vacuum. Some physicists call this idea wave-like dark matter. Instead of particles, the universe could be filled with quantum waves rippling across space, trillions of gentle vibrations, shaping galaxies like wind-shaped sand dunes. If this is true, then dark matter isn't hiding. It's flooding everything, softly, quietly. We just never learned how to feel it. Sometimes the biggest discoveries aren't things we catch, they're things we finally realize were already there. Fact 31. Galaxy rotation curves. Alright, imagine you're watching a merry-go-round. The horses near the centre move slowly while the outer ones move way faster. That's how galaxies should behave too. Stars close to the centre should move slower, and the ones near the edge should barely hold on. But here's the twist. When scientists actually measured galaxy rotation, they found something unexpected. The outer stars were moving just as fast as the inner ones. According to gravity, those distant stars should fly off into space, yet they stayed perfectly orbiting, as if something invisible was holding them together. That invisible something, dark matter. This moment in science was a huge revelation. If you think of a galaxy like a cosmic spinning disk, ordinary matter, stars, gas, dust, wasn't enough to keep it from tearing apart. There had to be more mass there, an unseen glue. The math kept shouting one thing: there's missing material, a lot of it. Suddenly dark matter wasn't just an idea, it became the leading explanation. No mystical force, no magic, just extra gravity coming from something we can't see. And ever since, astronomers have looked at spinning galaxies and thought, yep, something big is out there. Sometimes science isn't about what we see, it's about noticing what should happen and then asking why it doesn't. Fact 32. Gravitational lensing. Want to see gravity bend light like a magician bending spoons? That's gravitational lensing. It's one of the most elegant tricks the universe performs. When something massive sits between us and a distant star or galaxy, it warps space around it, and that bends light. The result? We see distorted, magnified, stretched images of whatever's behind it. A cosmic funhouse mirror effect. Now here's the cool part. Astronomers use this effect as a cosmic X-ray for invisible mass. If light bends more than expected, there must be extra gravity there, even if nothing is visible. Guess what keeps showing up in those invisible gravity maps? Dark matter. Every time light bends in unexpected ways, dark matter's fingerprints are all over the scene. It doesn't glow, it doesn't shine, but it pulls. And gravity never lies. What I love about this is how poetic it feels. We don't see dark matter, but we see how it touches light. It's like watching wind move leaves. You don't see the wind, but you see its work. Nature always leaves clues if you know where to look. Gravitational lensing tells us dark matter isn't a myth. It's shaping the universe, literally bending reality, even though we can't touch it. Fact 33. Bullet cluster proof. If dark matter needed a mic drop moment, the bullet cluster delivered it. Think of two galaxies smashing into each other, an enormous cosmic crash. Gas clouds slam together, heat up, glow in X-rays, but dark matter, it just keeps going, untouched, passing right through like a ghost army marching through fog. Scientists mapped the crash using gravitational lensing. The visible matter stuck in the centre, but the gravity, the mass, shifted to two separate blobs drifting away. That meant something huge and invisible moved through the collision, exactly where dark matter was supposed to be. It wasn't theory anymore, it wasn't speculation or fancy equations, it was observation. Clear, undeniable, chilling in its simplicity. Boom. Bullet cluster became one of the strongest pieces of proof for dark matter. And honestly, there's something eerie yet fascinating about invisible matter walking straight through cosmic chaos like it's taking a peaceful stroll. Fact 34. Cosmic microwave background patterns. If the universe had baby pictures, the cosmic microwave background, the ambience, would be one of them. It's the afterglow from the early universe, a faint radiation spread everywhere like the last warmth of a fire long gone out. But here's why it matters for dark matter. The CMB isn't smooth, it has tiny temperature bumps, tiny patterns that reveal what the early universe was made of. And those patterns don't match a universe made only of atoms and light. The numbers require extra matter, something that doesn't interact with light, something dark. Dark matter shaped those early ripples like fingers pressing into soft clay. Without it, the universe wouldn't have clumped into stars and galaxies later on. Everything would be too smooth, too simple. Dark matter gave the early universe texture. It's kind of amazing when you think about it. The proof of invisible matter sits frozen in the sky as ancient light, whispering the universe's first secret. Fact 35. Large-scale galaxy distribution zoom out. No, even more. Picture the entire universe like a giant 3D map. Galaxies cluster not randomly, but in enormous filaments, strands stretching millions of light years, like cosmic highways, and between them, immense empty voids. That giant web structure shouldn't exist without dark matter. It acts like a skeleton for the cosmos. Galaxies gather where dark matter gathers, space empties where dark matter is sparse. Without it, the universe would look almost featureless. Simulations prove it too. When scientists simulate universes without dark matter, everything collapses into boring blobs. Add dark matter back in, and suddenly, a cosmic web forms that looks exactly like what we see. The universe didn't just grow randomly, it followed an invisible blueprint, and that blueprint was drawn by dark matter. Maybe the universe is like a painting, and dark matter is the canvas we didn't know was there. Silent, hidden, holding everything up. Fact 36. Galaxy collisions reveal invisible mass. Let's imagine two giant cities drifting toward each other, except instead of streets and buildings, they're made of stars and gas. Galaxies collide slowly, like two clouds merging in the wind. Stars rarely crash into each other directly. There's just too much space between them. But gravity. That's where the drama happens. When galaxies collide, their gas clouds slam together and slow down. They heat up, glow, and get tangled like messy cosmic spaghetti. But something strange happens too. The gravity doesn't stay with the glowing gas. It moves ahead. Almost like the mass walks right through the crash without stopping. Think about that. The stuff we can see is stumbling and colliding, but the real mass, the heavier part shaping the outcome, keeps floating forward untouched. That's dark matter at work. It doesn't interact with gas or light. It doesn't get tangled. It just sails through, steady and quiet, dragging gravity with it like an unseen anchor. When astronomers map where the gravity ends up after a collision, they find most of it isn't sitting with the bright gas. It's off to the side, following invisible matter. That's not theory, that's observation. Collisions give the universe a chance to reveal what's normally hidden. Kind of poetic, isn't it? In the chaos of cosmic crash scenes, the invisible truth walks calmly through untouched, leaving a gravitational trail like footprints across the stars. Fact 37. Dwarf galaxies show strongest signs. Dwarf galaxies are the tiny cousins of big galaxies like our Milky Way. Picture galaxies the size of cosmic neighborhoods instead of sprawling star cities. And here's the wild part. These tiny galaxies are some of the biggest clues we have for dark matter. Why? Because dwarf galaxies are mostly dark matter with just a sprinkle of stars. They rotate too fast for the small amount of visible mass they contain. If you look at one, you'd think, wait, there aren't enough stars to hold this thing together. Yet they don't fly apart. Something unseen is keeping them intact. In fact, dwarf galaxies behave like dark matter bubbles with a few stars floating inside. Some astronomers call them dark matter labs, because they expose the universe's biggest secret in the simplest way. Less ordinary matter means the invisible stuff is easier to notice. Whenever scientists say, "Where is dark matter most obvious?" dwarf galaxies stand up like kids waving their hands in class. They shout the truth the clearest. Galaxies aren't held together by the glowing stuff, but by what hides in the dark. Funny how sometimes the smallest things tell the biggest stories. Fact 38. dark matter bridges between galaxies. This one feels like something out of a cosmic fantasy. Galaxies aren't lonely islands floating in space. They're connected, sometimes literally, by bridges of dark matter. We call these structures dark matter filaments. They stretch between galaxies like invisible ropes, binding cosmic structures together. Gas follows these bridges, flowing along them like rivers feeding galaxy growth. Stars are born because matter flows through these unseen channels. Occasionally, telescopes catch hints of these dark connections, a faint glow from gas trapped along a dark matter thread. It's as if the universe briefly highlights the edges of an invisible web, and when two galaxies tug on each other across millions of light years, the force often lines up perfectly with these hidden bridges. We don't live in a chaotic universe. We live inside an invisible architecture, a scaffold holding everything in place. Dark matter isn't dust scattered randomly. It is structure. It is design. It is the framework behind every galaxy and every cluster. Almost feels like the universe is stitched together with thread we can't see. Fact 39. Structure formation in the early universe. In the earliest moments after the Big Bang, everything was hot, energetic, and chaotic. Like a cosmic soup still boiling, ordinary matter was bouncing around so violently that it couldn't settle down to form anything stable. No stars, no galaxies. Just chaos. But dark matter, it didn't care about heat or light. It clumped quietly, forming little gravity wells everywhere, like tiny bowls in the fabric of space. And as the universe cooled, ordinary matter began falling into those bowls, gathering inside dark matter pockets. Those pockets grew. Small clumps merged into bigger ones. These became the first galaxies, then clusters, then entire cosmic superstructures. Without dark matter acting like the original backbone of the universe, nothing would have formed fast enough. The universe would still be a smooth, glowing fog with no stars, no planets, no life. Dark matter didn't just shape the universe, it started it. It created the scaffolding before anything else could exist. It's like the quiet builder who finished the foundation long before the lights ever turned on. We owe our galaxies and our existence to something we still can't see. Fact 40. Computer simulations match observations. Here's where everything gets excitingly real. Scientists build enormous computer simulations of the universe. They start with physics, the Big Bang, gravity, and then they add dark matter. They press run and watch a universe grow. What happens? The simulation forms a cosmic web identical to what telescopes see. Same galaxy shapes, same clusters, same voids. The universe on the screen looks like the universe outside. Then they try removing dark matter from the simulation. Suddenly everything looks wrong. No galaxy web, no realistic clusters. Everything collapses or spreads too far apart. It becomes a universe that doesn't look like ours at all. In other words, when we simulate the universe with dark matter, it looks real. Without dark matter, it falls apart. Computers don't take sides. They don't believe in theories. They just follow math. And the math keeps pointing one way. The universe is built on something invisible but powerful. We haven't touched dark matter yet, but we've watched it build a universe in virtual space. That's not just theory anymore. That's consistency across physics, observation, and simulation. And honestly, that gives the mystery even more weight. Fact 41. Why gravity alone doesn't explain it. Okay, let's clear up something many people wonder. If gravity pulls things together, maybe galaxies and universe behavior can be explained with just gravity. No dark matter needed, right? It sounds like a simple fix. But here's the issue. We did try that. Scientists pushed gravity to its limits, tweaked equations, explored modified theories, stretched the math, and still, the universe didn't behave correctly without dark matter. When we look at galaxies spinning, they move too fast for the gravity created by the visible stars alone. They should be flinging themselves apart like loose bolts flying off a spinning wheel, but they don't. Something extra is anchoring them, and in galaxy clusters, even more mass is missing. Gravity from visible matter isn't enough. The numbers don't add up. Yes, there are alternative gravity ideas like MOND, modified Newtonian dynamics, which try to change the rules of how gravity works at huge distances, but they struggle with other observations, galaxy clusters, gravitational lensing, cosmic microwave patterns. All of these demand extra mass. Think of it like hearing footsteps in an empty hallway. You can say, maybe it's just the house creaking. But when footprints show up and the floor bends and objects move, at some point you accept someone unseen is there. Gravity isn't wrong, but it's being pulled by more mass than we can see. Dark matter isn't just a theory trying to replace gravity, it's what gravity keeps pointing to. Fact 42. Particle colliders searching for it. Imagine the world's biggest machine, a circular underground tunnel so long it crosses countries, where particles are smashed together at nearly the speed of light. Sparks of new physics fly, detectors flash, and scientists watch, hoping to see something impossible. That's the Large Hadron Collider, LHC. One of its missions? Find dark matter. Why smash particles? Because dark matter could be created in these high-energy collisions. If dark matter appears, we wouldn't see it directly. We'd see energy vanish, as if something invisible grabbed it and ran. Think of fireworks exploding, and a piece disappears into thin air. It's exciting, but also humbling. We have the most powerful scientific machine ever built, and dark matter still hides. Maybe it's too heavy. Maybe it interacts too weakly. Maybe it's not a particle in the way we expect at all. But every collision is a question thrown at the universe, and every result, even silence, narrows the path forward. And somewhere in those bursts of energy, the answer may be waiting. Fact 43. Underground detectors hunting dark matter. Picture a dark, silent underground chamber deep beneath mountains or old mines. No sunlight. No noise from cosmic rays, just giant tubs of ultra-pure liquid or crystals sitting in absolute stillness. Why underground? To hide from everything that might make a false signal. These are dark matter detectors. They wait, patiently, for the rare moment a dark matter particle bumps into ordinary matter. Think of it like trying to catch a whisper in a hurricane. That's why they go beneath the earth, to remove the hurricane. Sometimes detectors flicker, a tiny spark, a signal, and scientists rush to see if it might finally be contact. So far, most signals fade into uncertainty, but each attempt gets sharper, quieter, more sensitive. We are listening harder than ever before. Dark matter might tap on one of those detectors someday, like a knock from outside the visible world, and when that happens, physics will change overnight. The most mysterious treasure hunt on Earth is happening far below our feet. Fact 44. Why dark matter rarely interacts. This part is both frustrating and incredible. Dark matter is everywhere, flowing through us, passing around us, shaping galaxies. Yet it barely interacts with anything. It doesn't bounce off atoms. It doesn't emit light. It doesn't get stuck, heated, or slowed down. It's like the ultimate introvert of the universe, present but quiet and distant. Why so shy? We don't know yet. Maybe it feels only gravity and nothing else. Maybe it uses forces we haven't discovered. Maybe it's made of particles that slip through space like ghosts. Ironically, this invisibility is what makes it real. If dark matter interacted normally, we would have found it long ago. Its silence is its signature. It behaves exactly like something that lives behind the curtain of reality, touching only the fabric of space-time, but not the bright stuff inside it. And that's what makes the mystery thrilling. The universe isn't just hiding secrets, it's telling us we don't yet know the rules. Fact 45. Dark matter streaming through Earth right now. Here's a thought that feels almost eerie. Dark matter is passing through your body as you read this, through your walls, through the entire Earth, constantly, silently, without stopping. We're moving through a cosmic ocean of it. The solar system orbits the galaxy, the Earth spins through space, and as we move, dark matter flows around us like wind through trees, except we can't feel it, see it, or hear it. No sound, no touch, no light, just a river of invisible mass pouring through our world. Billions of particles, if particles are what they are, streaming through you every second, not colliding, not interacting, just passing through, as if reality has layers and we only live in one of them. It's not science fiction, it's everyday physics, and if someday we find a way to sense it, not just infer it, humanity may learn that we've never been alone. The universe has always had silent companions swirling around us. We're just finally learning to notice them. Fact 46. Dark matter could pass through you every second. If I told you that something mysterious, invisible, and powerful is passing through your body right now, would you freak out a little? But don't worry, it's completely harmless, we think. Dark matter doesn't behave like normal matter, it doesn't bounce off you, it doesn't stick to you, and it definitely doesn't care about your personal space. It slips right through you like you're not even there, because in the physics sense, you might as well be invisible to it too. That's kind of mind-bending, isn't it? Imagine you're standing in a room talking to someone and suddenly you realise space isn't empty. The universe isn't quiet, it's busy. It's full of particles you can't see, can't feel, and can't stop, flowing like a silent cosmic river. Dark matter particles, assuming they really are particles, could be zooming through your body, through the walls, through the Earth itself every single moment. And you don't feel a thing, not even a tickle. Why? Because dark matter barely interacts with ordinary matter. That's why it's called dark, not because it's spooky, but because we literally cannot detect it directly. It ignores our atoms, our light, our electromagnetic forces. Gravity is the only thing that gives it away. It's like the universe's quiet introvert, always present, rarely noticed. Scientists think billions of dark matter particles pass through every square centimetre of Earth per second. Imagine a trillion tiny ghosts phasing through you at all times, and you never notice. Kind of makes your skin crawl, or maybe just your brain. And here's where it gets even more fun. Since dark matter moves through us constantly, some experiments are trying to catch it deep underground, where cosmic noise is low. It's like trying to net invisible fish in a dark ocean. So far, nothing. But that only fuels curiosity. Maybe one day someone will finally detect a dark matter particle. Maybe it'll be a giant breakthrough moment, like catching your first glimpse of a creature we only believed existed from footprints. Until then, you're living in a cosmic aquarium, fish swimming all around you, and you never knew. Spooky, right? Or beautiful? Maybe both. Fact 47. Why normal matter clumps? Dark matter shapes it. Think about every star, planet, mountain, tree, and cell that exists. Why didn't the universe just remain a floating cloud of loose particles? Why did matter clump together and create galaxies and worlds? One word: dark matter. Ordinary matter likes to interact, bond, and stick together. But in the early universe, everything was expanding rapidly, too fast for matter to gather and form structures on its own. Gravity alone from normal matter wasn't enough. There simply wasn't enough of it. Enter dark matter, silent architect of cosmic structure. While normal matter was bouncing around, light pushing it in every direction, dark matter was forming invisible gravitational scaffolding, a skeleton the universe could build on. These dark matter halos pulled ordinary matter toward them, like a magnet for gravity, helping it clump, cool, and eventually form stars and galaxies. You don't see dark matter, but you see its footprint everywhere. Every galaxy you look at sits inside a cloud of dark matter. Without that hidden foundation, our universe would be a smooth fog, not a cosmic fireworks show of galaxies. So in a way, dark matter didn't just shape the universe, it allowed you to exist at all. Without it, no stars, no planets, no life. Strange how the most important thing in the universe is the one we still barely understand. Fact 48. Could dark matter have its own forces? Now here's a twist. What if dark matter doesn't just exist quietly? What if it has its own physics, its own forces, maybe even its own interactions? Imagine a dark universe layered on top of ours, invisible, silent, but active in its own way. Maybe dark matter particles attract one another, or repel, or even form structures. Maybe they clump like normal matter. Maybe they have their own energy and their own version of electromagnetism, just invisible to us. It sounds wild, but scientists seriously consider this. Why? Because the universe is behaving in ways we still struggle to explain. Galaxies move strangely. Cosmic structures form in patterns that hint at deeper forces. So what if we're only seeing half the story? It's like listening to a conversation through a wall. You hear pieces, you sense movement, but you don't know the words. We see gravity acting, but maybe there's more happening. Forces we can't detect shaping a hidden world alongside ours. Some theories even suggest dark stars, dark planets, entire dark galaxies made of matter we'll never see but gravity says must be there. It's eerie, or exciting. Think about it. We might not be alone in the universe not because of aliens, but because there could be an entire shadow reality right next to ours, unreachable and unseen, and we're trying to crack the door to peek in. Fact 49. Some theories say dark matter can decay. Here's a strange idea. What if dark matter isn't forever? We think of dark matter as stable, ancient, part of the cosmic foundation, but some scientists believe it might slowly decay, not tomorrow, not in 1 billion years, more like across cosmic time. Imagine the universe losing its dark matter slowly, particle by particle. It would change gravity on huge scales. Galaxies could shift, clusters could loosen, cosmic structure could slowly unravel. Decay could also release tiny flashes of energy, subtle signals we might detect one day. In fact, a mysterious X-ray signal once sparked massive interest. Some thought it might be dark matter decay. Turns out, probably not. But the possibility remains. If true, dark matter isn't just a quiet backdrop. It's aging, evolving, playing a role in the universe's long-term story. And maybe one day, far, far in the future, the universe will look totally different because the invisible glue that holds it together slowly faded away. Even the unseen world isn't eternal. Kind of poetic, right? Fact 50. Dark matter may form dark atoms. Okay, now let's get imaginative. What if dark matter isn't just lonely particles drifting alone? What if it forms atoms like ours? Not hydrogen or carbon, but dark versions, dark protons, dark electrons, dark chemistry. That would mean dark matter might build structure, gas, clouds, stars, even planets, all invisible to us. It sounds like sci-fi, but physics doesn't forbid it. If dark matter has forces like electromagnetism, just hidden, then chemistry could happen too. A dark periodic table, dark molecules, a universe inside our universe, not interacting with us but evolving alongside us. No, this doesn't mean dark people live there. That's going too far. But the idea alone makes our universe feel so much bigger. What we see might be just the bright half of reality, like the lights in a city at night. Most of the world is still in shadow, and scientists are chasing clues, hunting little whispers of evidence, like detectives searching footprints in the dark. If we one day discover dark atoms, dark matter won't just be invisible mass. It will be a hidden kingdom of physics, and that changes everything. Fact 51. Could dark matter be hidden dimensions? All right, let's start with a question that sounds like it came straight out of a sci-fi movie. But scientists are dead serious about it. What if dark matter isn't matter at all, but the gravitational fingerprint of another dimension? Think about shadows. You don't actually see the thing casting the shadow, just the outline. Some physicists believe dark matter might be like that, not stuff floating around our universe, but the effect of something existing in hidden dimensions we can't access. We live in 3 dimensions, length, width, and height, plus time. But what if there are more, curled up tiny or stretched beyond our perception? Our universe could be a slice of something bigger, like a sheet in a cosmic book. Dark matter might be gravity leaking in from those unseen pages. Wild, right? Or maybe it makes perfect sense. If this is true, dark matter isn't just mysterious. It's a window, a clue that our universe is bigger and stranger than we ever imagined. It means our physics is only a chapter, not the whole book. And here's the spooky part. If gravity can cross dimensions, what else could? For now, we don't have the technology to peek behind that cosmic curtain, but just the idea that part of reality might be hiding right next to us, just out of reach, makes the universe feel alive with mystery. Sometimes science sounds like magic before we understand it, and maybe dark matter is the first knock on the door of another world. Fact 52. String theory predictions. String theory, you've probably heard the name. It's the physics idea that tries to be the theory of everything. According to it, the universe isn't made of tiny particles, but tiny vibrating strings of energy. And depending on how they vibrate, they become different particles. But here's where dark matter enters the story. String theory naturally predicts new types of particles. Particles we haven't discovered. Particles that barely interact with light or normal matter. Sound familiar? Some of those predicted particles fit perfectly with dark matter behavior. It also requires extra dimensions, which links back to the idea we just talked about. The universe in string theory isn't four-dimensional. It's more like 10 or 11. Dark matter could be a product of those hidden spaces, a kind of cosmic echo. The funny thing? For now, string theory is like a masterpiece puzzle we haven't finished. Pieces fit beautifully in theory, but proving it is like trying to take a photo of a dream. Yet every time dark matter puzzles us, string theory whispers, "Hey, I might have the answer." Whether it's right or wrong, it gives us something precious. Imagination backed by math. A way to think beyond what we see. In science, that's how revolutions begin. Fact 53. Parallel universe influence theory. Okay, buckle up. This one's deliciously mind-bending. What if the gravity we call dark matter isn't in our universe at all, but gravity from a parallel universe rubbing against ours? Picture two bubbles touching. They're separate, but pressure from one affects the other. Some physicists suggest our universe could be one bubble in a vast multiverse. If another universe sits close, even if we can't see it, its gravity might leak through, tugging on ours. From our perspective, that invisible pull looks like dark matter. This idea doesn't say there are alternate versions of you, though who knows? But it does suggest that our universe isn't alone. And dark matter might be the handshake between worlds. If that's true, then every time we talk about 27% of the universe being invisible, what we really might be saying is, another universe is touching ours, and we feel it. No telescopes can confirm that yet, but the thought alone gives the night sky a feeling, like there's more behind the stars than just emptiness. Maybe we're not living in the universe. Maybe we're living in a neighborhood. Fact 54. Emergent gravity alternative idea. Now here's a curveball. What if dark matter doesn't exist at all? Some physicists propose something radical. Gravity might not be a fundamental force, but an emergent phenomenon, meaning it arises from deeper laws of physics we haven't uncovered, like how temperature comes from billions of particles moving, even though temperature isn't a thing by itself. In this view, dark matter is just a sign that our idea of gravity is incomplete. Space has a hidden structure, like a cosmic memory or information field, and gravity changes depending on that structure. So galaxies don't rotate strangely because of invisible matter. They rotate strangely because gravity is doing something we don't fully understand yet. If this idea is right, then dark matter is like mist on a window. It looks real, but it's really a clue telling us to look deeper. Science isn't about locking onto one story. It's about staying curious enough to question even the rules. Fact 55. Modified Newtonian dynamics. MOND. Let's finish with one of the boldest ideas. MOND. Modified Newtonian dynamics. The name sounds complicated, but the idea is simple. What if Newton and Einstein gave us great gravity laws, but they don't work perfectly everywhere? MOND suggests that gravity behaves differently when it's extremely weak, like at the edges of galaxies. If you tweak gravity just a tiny bit at low accelerations, suddenly galaxy rotation makes sense without needing dark matter at all. A lot of scientists argue against MOND. It works beautifully in some situations, fails in others. But here's the beauty of science. Even wrong ideas can teach us something. MOND refuses to let us get lazy. It forces us to ask, do we understand gravity as well as we think we do? Some say dark matter wins the debate. Others say MOND isn't finished yet. Meanwhile, the universe keeps spinning its galaxies, not caring who's right. And for us? The mystery continues, and mysteries are where discovery lives. Fact 56. Fuzzy dark matter hypothesis. Let's start with a theory that sounds like it belongs in a sci-fi cartoon, but is actually serious physics. Fuzzy dark matter. No, it's not fluffy or made of cosmic cotton candy. The fuzzy part refers to wave-like behavior. If this theory is correct, dark matter isn't made of tiny particles at all. It's made of ultralight waves spread across galaxies. Imagine something so light and so gentle that instead of behaving like a particle, it behaves like a mist of quantum ripples. Instead of dark matter clumping into tight balls, fuzzy dark matter stretches and flows like a cosmic cloud. It smooths the universe out. It might explain why the centers of galaxies don't have sharp spikes of mass. They're soft and gradual, like waves fading on a beach, And here's a cool mental picture. If fuzzy dark matter exists, then the universe is not just filled with particles, but with giant quantum waves that stretch across space like invisible ocean currents. Kind of beautiful, right? Physics can be poetic too. The idea is still young. Experiments haven't confirmed it, yet. But it solves problems neat and clean, and in science, any theory that does that earns attention. Maybe the universe isn't built from cosmic dust. Maybe it's built from silent waves humming through space. Sometimes the simplest sounding name hides the deepest mystery. Fact 57. Is dark matter cold, warm, or hot? Alright, here's a cosmic temperature test. Yes, not about heat but speed. Scientists classify dark matter by how fast it moves. Cold dark matter, slow, clumpy, forms galaxies easily. Warm dark matter, medium speed, smoother. Hot dark matter, super fast, spreads out, doesn't clump much. So far, cold dark matter fits the universe best. It helps build galaxies the way we see them. Slowly, steadily, sticking together like cosmic clay. Warm dark matter is still on the table. It might fix small-scale puzzles, like why we don't see as many tiny galaxies as models predict. Hot dark matter? That one mostly failed. It spreads too fast to form galaxies at all. If dark matter were hot, the universe would look like one big smooth soup. No stars, no planets, no you. Funny, isn't it? The universe is structured because something invisible moved slowly enough to gather and build. Sometimes patience really does shape the world, even at a cosmic scale. Fact 58. Self-interacting dark matter possibility. Now imagine this twist. What if dark matter doesn't just float around ignoring everything? What if it interacts with itself? Right now, our leading picture says dark matter mostly just feels gravity. But some galaxies behave in ways that hint dark matter may bump, scatter, or push against other dark matter. Not strongly, not like billiard balls, but gently, like soft clouds brushing past. If true, dark matter has its own secret physics, its own rules, its own collisions. Why does this matter? Because it could explain why some galaxy cores look smooth, not dense, how galaxy shapes evolve over time, why small galaxies behave differently than big ones. It's like discovering water isn't just water. It has currents, tides, and waves. Dark matter may not be silent after all. Maybe it whispers to itself in a language we just can't hear yet. And suddenly, the invisible world feels a lot more alive. Fact 59. Could dark matter explain galaxy shapes? Look at spiral galaxies. Those elegant swirls like cosmic hurricanes frozen in space. Why do they look like that? Why don't they just blob into random lumps? Dark matter might be the sculptor. When galaxies form, stars and gas follow gravity. And if most of the gravity comes from dark matter, then galaxies are shaped by dark matter, halos like clay shaped by a hidden hand. Spirals, bars, disks. All these galactic designs may trace their origin to invisible architecture. Without dark matter, galaxies might wobble, warp, or fall apart. With dark matter, they settle into elegant, balanced shapes. Even galaxy collisions follow dark matter trails. Like deer paths in the woods. Where dark matter flows, galaxies follow. It's strange to think the universe's beauty, those swirling arms stretching across light years, might be drawn by something we can't see. Like an unseen artist carving patterns into the night. Fact 60. Maybe dark matter interacts only with itself. To end this batch, here's a simple but powerful idea. What if dark matter can interact, just not with us? Think of it like a world underwater. Fish communicate through currents and vibrations we barely notice. Dark matter may have forces and interactions, but only within its own realm. That would explain why we haven't caught it in detectors yet. It plays by its own rules. It doesn't shine, doesn't push electrons, doesn't heat up detectors, but it might collide, bind, even form structures in its own invisible sector. In that sense, dark matter isn't lonely or simple. It has a private life, a hidden physics club we aren't invited to, at least not yet. And honestly, that makes the universe feel so much bigger than our tiny senses suggest. We look at the stars and think we see everything, but maybe just maybe, we're only seeing the outlines, and the real engine of the universe hums silently, just out of sight. Fact 61. Dark energy pushes space apart. Imagine you're standing outside on a quiet night staring at the stars. Everything looks still, peaceful, almost frozen in time. But here's the wild truth. Space isn't still at all. It's stretching, expanding, and not calmly. It's being pushed outward. That push? That's dark energy. Think of the universe like a loaf of bread rising. Except the dough isn't just expanding. Something is actively stretching it, faster and faster. Dark energy isn't a force like gravity or friction. It's more like a pressure built into the fabric of reality, quietly inflating space everywhere at once. You can't point to a spot and say, there it is. Dark energy doesn't collect in places like matter does. It doesn't swirl or clump. It sits everywhere, pushing on space, stretching distance itself. Here's a bizarre thought. Galaxies aren't moving through space away from us. There's just more space appearing between us and them. And the more space there is, the more dark energy there is. Meaning the push grows stronger over time. It's like the universe has a runaway engine under its hood. Why does reality work this way? We don't know. Why is the universe accelerating instead of slowing down? Still no clue. But one thing is certain. Dark energy is the reason the universe isn't collapsing in on itself, but racing toward a wide, endless future. The cosmos isn't drifting apart. It's being pulled open by something we can't see, but feel through the movement of galaxies. A quiet, invisible hand, shaping the future of everything. Fact 62. Makes up the 68% of the universe. You ever feel like you don't know most of what's going on in the world? Well, the universe feels the same way about itself. Everything, stars, planets, galaxies, nebulae, black holes, you, me, every atom ever, makes up only about 5% of the universe. Dark matter takes another 27%. And dark energy, the invisible force stretching space, it claims a staggering 68%. Think about that. Most of reality is something we have never touched, never seen, can't interact with, and barely understand. We live in the tiniest piece of existence, confident we know so much, when really we've only just started flipping pages in the cosmic textbook. Even crazier, dark energy doesn't clump or cluster. It's everywhere, evenly spread out like a cosmic mist. The more the universe expands, the more of this energy fills space, and the more powerful its effect becomes. We don't know why the universe is made mostly of this stuff, but maybe that's the point. Discovery isn't about knowing everything, it's about realizing just how much is left to explore. The universe isn't mostly stars, it's mostly mystery. Fact 63. Discovered through supernova observations. Sometimes the universe surprises us in quiet moments. Scientists studying distant exploding stars and supernovae weren't trying to discover dark energy. They were measuring how fast the universe was slowing down. Except, it wasn't slowing down. Those supernovae were dimmer than expected, which meant they were farther away than they should be given the current models. The only explanation? The universe wasn't slowing. It was speeding up. Imagine throwing a ball into the air expecting it to fall, but instead it flies faster and faster upward. That's the moment astronomers realized something strange was happening. They double-checked, triple-checked, months of doubt. But the data held. That discovery shook physics. It wasn't supposed to happen. The universe had plans nobody predicted, and like that, dark energy stepped out from the shadows. Not with a bang, but with measurements, patience, and a whole lot of confusion. Science sometimes advances not with answers, but with one stubborn question. Well, that wasn't supposed to happen. Fact 64. Expansion of universe is accelerating. Picture two galaxies floating in space. They drift apart slowly, gently, not surprising. But now imagine that as time passes, their distance grows faster and faster, like someone keeps turning the dial up. That's the universe today. Every year, galaxies race away quicker than the year before. It's almost unsettling. Nothing in nature behaves like that. You throw something, it slows. You push something, it stops when you stop pushing. But space? Space seems determined to expand forever, fueled by something we can't see or touch. At this rate, distant galaxies are slipping out of view, not because they're moving, but because space is stretching too fast for their light to ever reach us. In the far, far future, the night sky may be almost empty, a universe growing cold, dark, and quiet. But we're not there yet. We're living in a rare moment, a universe still full of galaxies and wonder, before expansion isolates them forever. A cosmic dawn slowly drifting toward a lonely twilight. Fact 65. Dark energy fights gravity. Imagine two giants arm wrestling across eternity. Gravity and dark energy. Gravity pulls things together, stars into galaxies, galaxies into clusters, clusters into cosmic webs. Dark energy pushes them apart, stretching space, widening distances, loosening the cosmic glue. For billions of years, gravity was winning, building structure, making the universe dense and bright. But as space expanded, dark energy's influence grew. And now, dark energy is in the lead. Galaxies that once fell toward each other now drift apart. Gravity tries to hold the universe together. Dark energy gently, relentlessly pries it open. If gravity is the universe's builder, dark energy might be its quiet dismantler. Which force ultimately wins? That's still unknown. Maybe the universe will stretch forever. Maybe gravity will pull back in some future we don't yet understand. But for now, the cosmos isn't falling inward. It's opening wider and wider like a story still being written, page by expanding page. And somewhere inside all that motion, we exist. Tiny, but curious, watching the great forces of reality wrestle in the dark. Fact 66. Dark energy acts everywhere, all the time. Picture the universe as a giant balloon. Every tiny point in that balloon is being stretched, not just in some places, but everywhere at once. That's the strange, relentless nature of dark energy. Unlike gravity, which pulls locally, dark energy doesn't care about stars, planets, or clusters. It's uniform, omnipresent, and invisible, acting across the entire cosmos, quietly driving space itself to expand. Even in the emptiest voids, far from galaxies or any matter, dark energy is at work. It doesn't slow down. It doesn't need matter to exist. It's a constant background presence, like an invisible tide pulling the fabric of the universe apart. And that's part of what makes it so mysterious. It's everywhere, yet we can only infer it by observing the expansion of space and the motion of galaxies. Imagine walking in a gentle wind that touches everything equally, everywhere. That's dark energy on a cosmic scale, and it's been acting this way for billions of years, shaping the universe silently, steadily, and invisibly. Fact 67. Measured through the Hubble constant. The Hubble constant is like a speedometer for the universe. It tells us how fast galaxies are receding from each other due to cosmic expansion, and it's thanks to measurements of this expansion that we detect the presence of dark energy. Without it, the acceleration of galaxies would seem impossible. Astronomers measure the Hubble constant using multiple methods, observing supernovae, studying galaxy distances, and even analysing cosmic microwave background radiation. The results reveal something strange. The universe isn't just expanding, it's speeding up, and that acceleration points directly to the influence of dark energy. Think of it like tracking a car on the highway. If it keeps accelerating when there's no visible driver, you start to suspect an invisible force is pushing it. That's the universe in action, and the Hubble constant is our proof, quietly telling us that dark energy is real, pervasive, and powerful. Fact 68. Mystery behind cosmic acceleration. Here's the puzzle. For decades, scientists assumed that gravity would slow the universe down. Mass attracts mass, right? Yet when they measured distant supernovae in the late 1990s, they found the opposite. The universe's expansion is accelerating, not decelerating. This cosmic acceleration is a deep mystery. We can measure it, we can calculate it, and we can simulate its effects. But why it happens remains unknown. Dark energy is the name we give to the cause, but the true nature of it is still beyond our reach. It challenges our understanding of physics, space, and time itself. The universe is not just expanding, it's defying expectations. And every time astronomers look deeper, the question lingers. What invisible engine drives this unstoppable growth? Fact 69. the vacuum energy idea. One popular explanation for dark energy is called vacuum energy. In quantum physics, even empty space isn't truly empty. Tiny particles pop in and out of existence constantly, creating energy in the vacuum itself. That energy could act like a repulsive force, stretching space over vast distances. Think of it like bubbles forming in a calm pond, except the bubbles never stop and their effect grows the pond itself. This idea links the weirdness of quantum mechanics to the large-scale expansion of the universe. If vacuum energy is the source of dark energy, then every patch of empty space carries the seeds of cosmic acceleration. It's fascinating because it connects the tiniest scales, subatomic fluctuations, to the largest, the universe itself. From quantum foam to the accelerating cosmos, everything may be tied together by this invisible energy permeating space. Fact 70. Dark energy versus cosmological constant. Finally, let's clarify a subtle but important distinction. Dark energy versus the cosmological constant. The cosmological constant is Einstein's famous idea, a fixed, unchanging energy built into space itself. Dark energy, in general, is any force or effect causing the universe to accelerate. So the cosmological constant is one possible form of dark energy. If dark energy is exactly the cosmological constant, it's constant everywhere, forever. But some theories suggest it might change over time. Maybe it's dynamic, fluctuating, or even interacting with other cosmic components. Understanding this difference is crucial because it affects the ultimate fate of the universe: eternal expansion, eventual slowdown, or something even stranger. In short, dark energy is the phenomenon. The cosmological constant is one possible explanation, and until we can probe it directly, both remain central mysteries at the heart of modern cosmology. Fact 71. Einstein's cosmological constant returns. When Einstein first developed general relativity, he added a term called the cosmological constant, a mathematical extra force to keep the universe static. At the time, everyone believed the cosmos was motionless. But then Edwin Hubble discovered the universe was expanding, and Einstein reportedly called the constant his biggest blunder. Once expansion was confirmed, there seemed to be no need for it. The universe didn't need help staying balanced. It was already in motion. Over 70 years later, something extraordinary happened. Astronomers discovered that the universe isn't just expanding, it's accelerating. Space is stretching faster and faster. Suddenly, Einstein's discarded idea came back into play. The cosmological constant was reborn, now interpreted as dark energy, an inherent push built into space itself. This resurrection is one of science's most poetic twists, a discarded idea that returned to explain the greatest mystery in the universe. It suggests that empty space has energy, an invisible pressure woven into the fabric of space-time. Einstein tried to balance the universe. Instead, he predicted its runaway future. The cosmological constant remains one of the simplest and most powerful explanations for dark energy, a steady force, unchanging, calm, and everywhere. Yet simplicity doesn't mean certainty. We still don't know why it exists, why it has the strength it does, or whether it truly represents reality. Einstein created it for the wrong reason, removed it. Then the universe brought it back for the right one. Sometimes even a blunder reshapes science forever. Fact 72. Quantum vacuum fluctuation theory. Even empty space is not really empty. According to quantum physics, the vacuum is alive with flickering particles, appearing and vanishing faster than we can measure. This restless, buzzing ocean of quantum fluctuations may hold the key to dark energy. The idea is simple in concept but wild in implication. These tiny fluctuations create a subtle push that stretches space itself. The vacuum pushes outward. Imagine a pot of water quietly boiling at a microscopic level, bubbles forming, collapsing, and reforming constantly. The space between galaxies might behave like that, except instead of bubbles, it's energy pulses. This energy builds up across the cosmos like pressure in a balloon. The universe expands not because something is pushing from outside, but because space itself produces expansion from within. However, there's a catch, a big one. When physicists calculate this vacuum energy, the theoretical value is outrageously wrong, off by a factor of 10 to the 120. the biggest mismatch between theory and observation in science. Nature seems to use only a tiny drop of the predicted amount. Why? We don't know. Something about the vacuum remains hidden. This theory ties together the two greatest frameworks in physics, quantum mechanics and relativity, yet they disagree violently here. Dark energy might be the bridge we need to unify them, the cosmic whisper revealing where our understanding breaks. Fact 73. Phantom energy idea. Dark energy may not just push, it might pull space apart violently. Phantom energy is a theoretical form of dark energy that grows stronger over time. Instead of remaining constant, its power increases as the universe expands. This could lead to a terrifying fate called the Big Rip. In a phantom energy universe, galaxies don't just drift apart. They are torn from each other. Trillions of years from now, galaxy clusters would shred into individual galaxies, then stars would drift apart, then planets would lose their orbits. Eventually, gravity itself would weaken under the growing force, atoms would rip apart and space-time would unravel. The universe would end not in collapse but in dissolution. It sounds like science fiction, but it's a real possibility accepted by cosmologists. Phantom energy is speculative, but it fits current observations just well enough to remain plausible. It's the most dramatic version of dark energy, not a quiet pressure, but a growing force destined to erase cosmic structure. If true, dark energy is not gentle, it's a ticking cosmic countdown. Thankfully, if this fate awaits, it is far in the future, trillions of years ahead. Still, phantom energy reminds us that we do not control the narrative of the universe. We only observe, wonder, and wait. Fact 74. Quintessence. Changing field theory. Not all theories treat dark energy as constant. Quintessence proposes that dark energy is a dynamic field, a force that evolves over time, like a slow-moving cosmic tide. Unlike the cosmological constant, quintessence has a personality. It can grow, weaken, or interact with the universe in different ways throughout history. Imagine a fluid that fills space, flowing gently and shaping distant galaxies without touching matter directly. In the early universe, this energy field may have been weaker. Today we see its strength more clearly because space has grown. In the far future, who knows? Quintessence may fade, strengthen, or even reverse, potentially slowing expansion instead of speeding it. If quintessence is real, dark energy is not a simple constant. It's a living component of the universe, gradually evolving. Physicists search for subtle shifts in expansion speed across cosmic time to detect this. A change would be revolutionary. It would tell us that dark energy is not a fixed property of space, but a field we have yet to understand, similar to electromagnetic or gravitational fields. Quintessence gives dark energy freedom, and perhaps intention. Not a static force, but a cosmic actor with its own story. Fact 75. Multiverse dark energy levels. One idea stretches imagination to the edge. Dark energy might differ from universe to universe. In a multiverse, countless universes may exist, each with its own physical rules, different gravity, different particle masses, different dark energy strengths. We find ourselves in a universe where dark energy is small but positive, allowing galaxies, stars, and life to form. Some theorists argue that most universes in the multiverse wouldn't be so lucky. Too much dark energy, and everything expands too fast. No stars ever form. Too little, and the universe collapses before it begins. We live in the rare cosmic Goldilocks zone, where dark energy is just right for life. This is not a testable idea, yet, but it explains a deep puzzle. Why does dark energy have the strange value it does? Why this number and not another? The multiverse offers one possibility. We exist in a universe where observers can exist. That's not mystical. It's survival bias on the grandest scale imaginable. Dark energy might not just shape our universe. It might define why we are here in this universe at all. Fact 76. Extra-dimensional gravity theories. Let's start with an idea that sounds like it rolled straight out of a sci-fi movie. Yet scientists take it seriously. What if dark energy isn't a mysterious force at all, but simply gravity leaking into extra dimensions? Imagine our universe as a flat sheet, floating in a much larger space. We live on that sheet. We feel the forces on it. We move across it. Everything we know exists on it. But there could be other sheets, other layers, other directions our senses can't detect. In theories like brain cosmology, gravity is allowed to stretch into higher dimensions while light and matter stay trapped in our brain. That means what looks like weak gravity in expanding space might just be gravity spreading thin across realities. Instead of the universe accelerating because of some invisible pressure, maybe we're watching the effects of dimensions we cannot see. This kind of model tries to solve two puzzles at once: dark energy and why gravity is so much weaker than other forces. If gravity can wander off into extra dimensions, no wonder it feels faint here. And if the structure of those dimensions changes over time, space expanding faster could be the natural result. We don't have proof yet, but it's a reminder. Sometimes the universe isn't hiding new forces, it might be hiding directions. Fact 77. Holographic universe models. Picture a hologram, a flat sheet that contains information to create a 3D image. Now imagine the entire universe working like that. According to the holographic principle, everything we experience in 3D, space, stars, planets, galaxies, even you, might be encoded on a distant cosmic boundary like the surface of a sphere. Wild, right? But this idea isn't just dreamy philosophy. It comes from black hole physics. Stephen Hawking and others discovered that a black hole's information seems stored not inside its volume, but on its surface. That inspired physicists to wonder if all of space works this way. In this view, dark energy might not be a force inside the universe at all. It could be a side effect of how information stretches or evolves on this cosmic boundary. As the universe gets bigger, the holographic information changes and expansion speeds up. It's hard to imagine because our senses are trapped inside the projection, but holographic models offer a deep connection between gravity, quantum theory, and information. If they're right, understanding dark energy may require understanding not space and matter, but the cosmic code beneath them. Sometimes reality hides behind its own illusion, and we just haven't learned the trick yet. Fact 78. Could dark energy decay someday? We think of dark energy as eternal, steadily pushing space apart. But what if it's temporary? Some theories say dark energy could fade, weaken, or transform in the future, like a battery that slowly drains. If dark energy decays, the universe's fate changes completely. Expansion might slow and eventually stabilize. Maybe galaxies would still drift, but not endlessly. In some extreme models, decay could even allow gravity to reclaim control someday, pulling everything back together in a big crunch. There's also the opposite scenario. If dark energy transforms into a new kind of field, expansion could change again, maybe even leading to cycles of growth and collapse, a universe breathing across eons. We look at ancient light, supernova data, cosmic microwave maps, to see if dark energy has changed over billions of years. So far it seems steady, but measurements have hints of slight differences that could point to evolution. The truth might be quiet and slow, like erosion shaping mountains. But in the end, it would decide the universe's final chapter: endless expansion, rebirth, or collapse. One day, dark energy may end, and something else may begin. Fact 79. Variable dark energy theories. Not all dark energy theories agree on a constant force. Some suggest it's dynamic, changing its strength over time or reacting to cosmic conditions. Think of it like weather rather than climate, not fixed but shifting slowly. If dark energy varies, early cosmic history might have looked different. Stars formed, galaxies merged, clusters grew, and in the background, the universe's pressure changed bit by bit. This could explain why some measurements of the universe's expansion don't line up perfectly today. Maybe the mismatch, the Hubble tension, is the universe whispering that dark energy isn't static. Imagine a dial slowly turning over billions of years. Today it's set to gentle acceleration. In another era, it could have been weaker or stronger. In the deep future, it might change again. Variable dark energy brings flexibility to cosmology, a universe not built like a machine with fixed gears, but a living system with evolving forces. If dark energy has moods, then cosmic history is more dramatic than we ever imagined. Fact 80. Dark energy and inflation connection. Long before stars, galaxies, or atoms, In the first split second of existence, the universe experienced inflation, a burst of expansion so fast nothing in human experience can compare. Space grew faster than light, stretching tiny quantum fluctuations into the seeds of galaxies. That early inflation looks eerily similar to dark energy today. Both stretch space. Both act like pressure built into the vacuum. Both seem to come from fields that don't behave like normal matter. So here's the big question. Are they connected? Maybe the force that blew up the early universe is a cousin of dark energy, or even the same phenomenon revived at a weaker level. The beginning and the future might be tied by a single strange engine hidden in space-time, or perhaps inflation shut off and dark energy turned on billions of years later, like two cosmic stages in a play. But the similarity is too strong to ignore. Understanding one might solve the other. When we look deep into space, we see ancient light and the future written together. The universe began in a burst of expansion, and it may end in one too. Fact 81. Dark energy will dominate forever? Maybe. Here's a sobering thought. If dark energy keeps its grip, it will dominate the universe forever. Gravity, stars, black holes, they may matter now, but over trillions of years, the push of dark energy could overwhelm everything. Galaxies will drift apart, clusters will stretch, and the cosmos will become an ever-thinning web of isolated stars. Of course, we say maybe, because dark energy might not be constant. It could weaken, fluctuate, or even disappear. But if it persists as it is today, it becomes the universe's ultimate ruler, shaping the fate of all cosmic structures. The universe isn't just expanding, it's heading toward a future where dark energy sets the rules. It's a reminder of scale. Right now, we feel safe in our little corner of the Milky Way, but on cosmic timescales, dark energy is the quiet force writing the long-term story. Fact 82. The universe may expand faster and faster. Every galaxy, every cluster, every distant supernova is part of a larger cosmic ballet. And the rhythm is accelerating. That's the signature of dark energy. Expansion speeding up over time. It's not linear. Space itself stretches more rapidly as the universe grows. Picture drawing dots on a balloon and inflating it. At first, the dots move slowly apart. Then, as the balloon stretches, the distance between them grows faster. Now imagine that balloon growing forever, with its surface accelerating outward endlessly. That's the universe today. Galaxies that seem close might eventually slip beyond view because space is stretching faster than light can travel between them. Acceleration may continue indefinitely, shaping the ultimate geometry and destiny of the cosmos. It's a cosmic race where dark energy keeps pressing the gas pedal. Fact 83, heat death prediction, energy spreads thin, long term, dark energy hints at a grim fate, heat, death. As the universe expands, energy spreads out, stars burn out, galaxies drift apart, black holes evaporate, and eventually the universe reaches a state of maximum entropy, a cosmic equilibrium where no work can be done. Heat death doesn't happen in a sudden flash. It's a slow, inexorable cooling, a quiet fading of all structure and activity. Matter exists, but nothing meaningful can occur. It's the universe's version of eternal silence, a final, frozen state where motion and life as we know it are impossible. It's hauntingly beautiful. The universe doesn't explode or collapse, it simply runs out of usable energy. The heat death scenario is the ultimate slow fade, dictated by the persistent push of dark energy stretching everything thin. Fact 84. Big Freeze Scenario. Closely related to heat death is the Big Freeze. Expansion driven by dark energy means galaxies move apart faster than light can bridge the gaps. Eventually, distant galaxies will disappear from view. Stars will die, leaving behind white dwarfs and black holes. Space itself becomes empty and dark. From the perspective of any remaining observers in the far future, the universe may look almost lonely, only a few local stars in an endless void. Planets lose their heat, atoms slow their dance, and radiation spreads thin. The Big Freeze is quiet, inevitable, and profoundly vast. It's not dramatic like a collision or explosion, but in its emptiness, it's a final testament to dark energy's relentless influence. Fact 85. Big Rip Scenario. Galaxies torn apart. Now for the most dramatic vision, the Big Rip. Some theories suggest dark energy could grow stronger over time, not steady but increasing in intensity. In that case, the expansion eventually overcomes every force holding matter together. Galaxies would disintegrate first, stars and solar systems would fly apart, even planets would tear apart under the overwhelming cosmic pressure. Finally, atoms themselves could be ripped to pieces as space-time stretches infinitely fast. The Big Rip is the ultimate display of dark energy's power, a universe literally torn apart at every scale. Unlike the quiet Big Freeze, this ending is violent and complete, leaving nothing bound together. Whether it's a slow fade or a violent tear, dark energy dictates the ultimate fate of the universe, and for now, we're observing the first signs of its unstoppable influence, wondering what the far future holds in its invisible grip. Fact 86. Dark energy may weaken and reverse expansion. Not all dark energy theories assume eternal acceleration. Some propose that over trillions of years, dark energy could weaken, losing its cosmic grip. If that happens, gravity might slowly regain control over the universe's expansion. Imagine the cosmic tide slowing, then stopping, and eventually beginning to pull everything back together. This scenario flips our current expectations. Galaxies that are now drifting apart might start moving closer, galaxy clusters could merge again, and the universe might enter a contraction phase. Dark energy, the invisible hand stretching space, would have lost its dominance. The ultimate fate of the universe would be rewritten, a reminder that even cosmic forces may not last forever. Fact 87. Possible Big Crunch return. If dark energy fades or reverses, the universe could experience a big crunch. This is the opposite of the Big Bang. Instead of exploding outward, all matter and energy collapse back into an extremely dense state. Galaxies collide, stars spiral inward, and space itself contracts. The Big Crunch is dramatic and catastrophic on a cosmic scale, but in a strange way it mirrors the origin of everything. The universe might end as it began, compressed into a singularity, perhaps setting the stage for a new expansion. Some cosmologists even speculate that the Big Crunch could trigger another Big Bang, creating a cyclical universe. The idea reminds us that the universe's story may not be linear. Expansion and contraction could alternate, giving the cosmos a kind of heartbeat across unimaginable timescales. Fact 88. Could the universe oscillate forever? Building on the Big Crunch idea, some theories propose a cyclic or oscillating universe. Expansion and contraction repeat endlessly. A Big Bang, billions of years of growth, dark energy fades, gravity pulls everything together, a Big Crunch occurs, and then another Big Bang begins. If true, dark energy's current acceleration is just one phase in a grand cycle. The universe might have no true beginning or end, only alternating epochs of creation and destruction. Stars, galaxies, and observers like us appear and vanish in each cycle, while the cosmic rhythm continues quietly behind it all. It's a humbling vision, the universe as a timeless dance and dark energy merely one step in an eternal choreography. Fact 89. Future galaxies will disappear from view. Even if the universe never contracts, dark energy ensures a lonely cosmic future. Galaxies beyond our local group will drift so far away that their light can never reach us. The night sky, which now dazzles with countless stars, will gradually empty. Future civilizations, trillions of years from now, may see only a handful of nearby galaxies. The vast majority of the cosmos, full of distant clusters and clusters of clusters, will vanish from view. Dark energy doesn't just stretch space, it isolates objects from one another, leaving cosmic islands in a dark, expanding ocean. In that sense, the universe is already preparing its ultimate curtain call. Fact 90. Most stars will fade into darkness. The endgame is clear. Stars, the shining beacons of galaxies, will eventually exhaust their fuel. Massive stars explode as supernovae and leave behind black holes or neutron stars. Smaller stars burn out slowly, becoming dim white dwarfs, then cooling over trillions of years into black dwarfs. In a universe dominated by dark energy, these remnants will drift farther and farther apart. Light itself will grow scarce. The cosmos will transition from a lively, glowing spectacle to an almost completely dark void. Even if the universe persists forever, it will do so quietly. Energy spreads thin, matter fades, and the cosmos becomes a cold, dark expanse, a silent testament to the unstoppable influence of dark energy. Fact 91. James Webb Telescope contributions. The James Webb Space Telescope, JWST, isn't just about stunning pictures of galaxies and nebulae. It's also a key tool for understanding dark energy. By observing distant supernovae and galaxies billions of light-years away, JWST helps scientists measure the universe's expansion with unprecedented precision. The farther we look, the further back in time we see. JWST captures light from the earliest galaxies, revealing how cosmic expansion has changed over billions of years. This allows researchers to test dark energy theories, check if it's constant, or detect subtle changes over cosmic history. JWST's infrared capabilities are crucial because much of the light from the early universe is redshifted into longer wavelengths. With these observations, we can map the growth of cosmic structures and indirectly track the influence of dark energy on galaxy formation. In essence, JWST isn't just a telescope, it's a time machine helping us understand how dark energy shaped the universe across billions of years. Fact 92. Euclid Space. Telescope mission. The Euclid Space Telescope, launched by ELM, is designed specifically to explore the dark universe. Its mission: map the distribution of dark matter and dark energy across billions of light-years. Using weak gravitational lensing and galaxy clustering measurements, Euclid creates a three-dimensional map of cosmic structures, revealing how matter and energy interact. Why is this important? Because dark energy isn't something we can see directly. Instead, it affects the motion of galaxies and the growth of cosmic structures. By carefully measuring these effects, Euclid can test competing dark energy theories, determine whether it's constant or dynamic, and even look for hints of new physics. Euclid's observations will complement telescopes like JWST, giving a broader, statistical view of the universe. Together, these missions create a more complete picture, helping scientists constrain dark energy's properties and better understand the fate of the cosmos. Fact 93. Vera Rubin Observatory mapping dark matter. The Vera Rubin Observatory is named after the astronomer who provided some of the earliest evidence for dark matter. While its primary mission is wide-field surveys of the night sky, it's invaluable for dark energy research as well. By tracking millions of galaxies over time, the observatory can study cosmic expansion and gravitational lensing effects, indirectly probing both dark matter and dark energy. Its data will measure how structures grow under the competing influence of gravity and dark energy. More precise maps of galaxy clusters and cosmic filaments allow scientists to test models of dark energy and see whether it behaves as a cosmological constant or varies over time. With its massive data collection, the Vera Rubin Observatory will create a detailed dynamic map of the universe, a key tool for unraveling how unseen forces shape the cosmos. Fact 94. Large Hadron Collider experiments. The Large Hadron Collider, LHC, at CERN is famous for discovering the Higgs boson, but it also contributes to understanding dark matter and dark energy. While dark energy itself is a large-scale cosmic phenomenon, LHC experiments probe the fundamental particles and forces that may be linked to dark matter, which in turn is closely connected to dark energy in cosmological models. By searching for exotic particles, supersymmetric partners, or unknown interactions, the LHC provides insights into the hidden sectors of physics. These experiments help test theories that may explain both the missing mass in the universe and the mysterious energy driving expansion. Essentially, the LHC digs into the smallest scales to illuminate the largest mysteries. Fact 95. NASA and ESA Dark Energy Surveys. NASA and ESA have launched multiple surveys to study dark energy, including projects like WFIRST, Roman Space Telescope, and Large Sky Surveys. These missions focus on supernovae, galaxy distributions, and gravitational lensing to measure cosmic acceleration and test dark energy models. The goal is to understand not only how fast the universe is expanding, but whether that expansion is changing over time. Are we looking at a cosmological constant, a dynamic field, or something entirely unexpected? These surveys provide the statistical power to answer those questions, combining precision measurements with massive data sets. Together, NASA and ESA efforts create a global network of observations, each contributing pieces of the puzzle, helping scientists tackle one of the greatest mysteries in modern physics: why the universe is accelerating and what dark energy really is. Fact 96. Neutrino experiments and dark matter links. Neutrinos are some of the most elusive particles in the universe. Tiny, nearly massless, and barely interacting with anything. Because of their ghostly nature, they've become a focus for understanding dark matter. Some theories suggest that a type of neutrino, called a sterile neutrino, could account for at least part of the unseen mass in the cosmos. Experiments around the world, from Japan's Super Kamiokande to Fermilab in the US, track neutrinos to test these ideas. By studying how neutrinos oscillate and behave, scientists hope to detect anomalies hinting at connections to dark matter. It's a long shot, but neutrinos might provide the first tangible evidence linking the invisible particles to the structure of the universe. In essence, tiny, nearly invisible neutrinos could hold clues to the largest invisible component of reality, a cosmic paradox of scale and subtlety. Fact 97. AI simulations of cosmic structure. Understanding dark matter and dark energy isn't just about telescopes and detectors, it's also about supercomputers and AI. Simulating billions of galaxies over billions of years requires immense computational power. AI helps scientists model cosmic evolution, test theories, and predict how dark matter and dark energy shape the universe. These simulations allow researchers to compare virtual universes with the real one. Why do galaxies rotate the way they do? How do clusters form under unseen influences? AI identifies patterns and anomalies that human eyes might miss, refining our understanding of the dark cosmos. Without these simulations, we'd have observational data, but no way to connect the dots across such enormous scales. AI acts like a cosmic detective, reconstructing invisible forces from the evidence they leave behind. Fact 98. Underground laboratories around the world. Detecting dark matter directly is incredibly tricky. Ordinary particles interact constantly, but dark matter barely interacts at all. To reduce interference from cosmic rays and background radiation, scientists place detectors deep underground, in mines, mountains, and tunnels. These laboratories, from Italy's Gran Sasso to the Sanford Underground Research Facility in the US, host ultra-sensitive instruments designed to catch the rare particle interactions. They're quiet, shielded, and isolated, essentially listening for whispers from the dark side of the universe. Every tiny signal is analysed, filtered, and cross-checked. A single detection could confirm decades of theoretical work. It's painstaking, patient work, a testament to humanity's determination to uncover the invisible. Fact 99. Dark matter direct detection efforts. Direct detection experiments aim to observe dark matter particles interacting with ordinary matter. Technologies like liquid xenon detectors, crystal arrays, and bubble chambers attempt to catch the weak collisions of dark matter particles passing through Earth. So far, nothing definitive has emerged, but each experiment narrows down the possibilities, ruling out some candidates and focusing the search. Even a null result is valuable. It tells physicists which theories are viable and which aren't. It's like looking for a ghost in a vast mansion. You may never see it, but careful observation reveals where it cannot be. Each step brings us closer to understanding what comprises nearly a third of the universe. Fact 100. Humanity may solve it, or uncover deeper mysteries. We've reached the final fact, and it's humbling. Humanity may one day uncover the nature of dark matter and dark energy, finally explaining 95% of the universe. But there's a twist. Solving one mystery may reveal countless others. The universe has a way of surprising us. Every experiment, telescope, and simulation may answer a question while opening new doors we didn't even know existed. Dark matter and dark energy might lead to entirely new physics, new particles, or hidden dimensions. For now, they remain the greatest cosmic mysteries. But we are looking, probing, measuring, and imagining. And that pursuit, the search itself, is one of humanity's most remarkable adventures. The invisible dominates our universe, yet curiosity drives us to understand it. And maybe, just maybe, the next discovery will change not only what we know about the cosmos, but how we see ourselves in it.